Hello, in this video we'll look at a NES challenge that is called Space Fights. The challenge can be found on this GitHub and it's also released with a source code, but of course for now we'll not look at the source code. We'll try to analyze it ourselves and see if we can get a flag. So I just download this NES file. I have it locally. But before we start analyzing it, maybe let's try to run it and see if it even runs and we have anything to look at. So I will be using this no NES or no SNES, how it's called, debugger. It's quite nice. It has a very nice debugger. I like it. So yeah, this is what I've been using. So let's just load the file into the debugger. And the file starts and we can see some text scrolling, and that stops. Let's try to run it again. Yeah, the same effect. So I guess I don't see any flag here, so we'll need to find out maybe later how we can get to print the flag. Maybe we need to press some key combination or something else. But for now we can close it, and let's try to load the file in Ghidra. So I have already prepared a Ghidra project, so I'll just import the file. And the first challenge in this challenge is that we need to actually pick a language, because it's not pre-selected. The file is a complete ROM, and there is no information about the language that Ghidra can pick up. But there is a very good wiki about NES development, wiki.nesdev.com, and we have both the file format described here as well as a lot of other information. And we can go to the main page actually here, and we can from here can see that the CPU is modified 6502. So let's just pick that at our language selector in Ghidra. So 6502, and we have it on the list and we can pick up. Okay, so we imported the file. Now we can open our disassembler and we could start analyzing the file now, but I think it doesn't make sense that much, because we need to prepare Ghidra a little bit. At least I think we could do it after the analysis, but we don't need to waste time for analysis. So I'll press no, and first what I will do, I'll go to this memory map, and this is how our file being mapped. So we have this section RAM. It starts from 0, ends at this address, it has its length, and its source is a file. But the file is not just the code. There are some headers and some additional information, and we can also learn about the file format from the NESDev wiki. So this is the file format. We have a header 16 byte, then there is a trainer if present. In our case we don't have it, and then program data. So this is what we are actually interested in, this program ROM data. So it will start in our case from byte 16. So we need to prepare a little bit Ghidra to point this information to the correct place, and we can do it from this memory map too. So we could actually carve out data from this file. So actually there's like two ways. We can either remove it and add additional new section based on the file, or we could just split it and move it. I don't know which is, I guess, faster is just to remove it and add a new section. We'll give it a name RAM. It will start from, for now, let's start address 0. It will has 8000 hexadecimal bytes. It will be that long, and it will be based on the file bytes. But we need a file offset. So file offset is 60. Okay, and that gives us that the header will be skipped, But it's not enough, because if we also look at the wiki, at this CPU memory map, we'll know that the program data is actually somewhere in those addresses. And also here it says that most common it's at 8000 hex. It's the usual ROM. And we can also confirm that if we see in our debugger, we were actually at addresses 8K. So we can safely assume that this is our base address, so 8000 hex. So in Ghidra, to have that, we need to move this segment or block. So we use this move block to another address, and we just add put 8K and just OK. And now everything is fine. So we can close it and we can actually start disassembly. So I'll just select everything and just press D for the disassembly. And now the code looks almost okay. We can still see some red stuff here because we don't have any block mapped in those addresses. So there is like a 2K range and 4K range that are not mapped because, well, we didn't add blocks for those addresses. So we can do that now. So let's just open memory map again and we'll add a new block. And let's see what actually Wiki says about those addresses. So at 2K, there is this NES PPU registers. So let's just add that. So we'll call it PPU. It will start at 2. It will have a length of 8. And let's just keep it uninitialized for the moment. And if we save that and go back to our Ghidra, we can see already those addresses are okay. So they are not red, but there are still those at 4K are red. So let's just see what we have there. So at 4K till 418, we have those APU and IO registers. We can check what this APU is. This audio processing unit, and we can read about what our specific registers are responsible for. But for now, we don't need that. So let's just add this block in Ghidra so we don't have those red addresses visible. So again, we'll use our window. So PPU, no, not PPU, APU. And it will start at 4 and the size was 18 and also uninitialized, that's fine. And now we should, at least all of those red that we saw here should be gone, and it looks like they are gone. Okay, so that's, yeah, we already see some stuff here also red, so maybe let's just see what we could do also with those addresses. So those like at 0 hex address. So again, our wiki, and we have that from 0 to 7FF, we have this 2K internal RAM. Yeah, so let's just set it. And it actually, we have mirror, so it's actually from 0 to 2K, it's being mirrored 4 times. So let's just set 2K of those. What was the name? Internal RAM. Let's call it internal. It starts from 0. It's 2K and it will be uninitialized also. Okay, and it sounds like, okay, it's getting better, our memory map. And we should not have now, okay, everything should be covered, nothing should be in red. Here it's also, there are some red, Ghidra points out, but it looks okay. Okay, so now we have Ghidra prepared. So let's just start analyzing. So the code starts at this address 800. So we can just create like a function here. So just press F and it will create a function. And if we have a function, we'll be able to also modify it here. So this is our main function. Oh, I'm not sure if we can call it main, but maybe let's call it entry function. And this is what some stuff is happening in our game or program, and you can see some addresses here. So it's like this 340, 341, 342, 344, and that's like quite interesting. We don't know what they are yet, but what we could do, we could see what values are actually being put in those addresses during the execution. This is sometimes quite interesting to see how the values are being changed. So you don't have to analyze the source code, you can just analyze what data is there, and based on the data we can also find out what is actually going on. So let's again open our program, and maybe let's scroll to those addresses here in this section where we can see the memory. Let's maybe, I don't know, okay, I can make it a little bigger. So 340. So this is the addresses that we are doing something in this code in Ghidra, and we can already see that this looks quite interesting. There's like a lot of variety of bytes, so it's not some pattern being repeated, so we can assume that something interesting going on here. So let's just reset again, and let's just observe those bytes, and we can immediately see that this byte is being increased, and at some point it stops. And let's just again look at the screen and this value. So we can see that this value actually stops if we finish writing what we want to write. So we can assume that this address 34, and this is 012, 342 is some kind of line number that we are printing. We could actually rename it in Ghidra like line number, and we can already have some information a bit clearer. So okay, we identified that something, this 342 could be a line number, and we can see that there's some comparison that line number is less than data 319. So maybe let's see what we have at address 319 in the debugger. So it's the same region, but it's like this line, and we could just count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 64. Interesting. This is the same 64 as we can see. Not the value is the same. 64 here, 64 here. So maybe it's actually we display as many lines as the value that we have here. So maybe if we modify it to some bigger value, we'll be able to display more lines than just those that we see. So let's just try that. So let's just reset again and break before we finish displaying. So we are already at line 15. So let's just modify this to, I don't know, let's start small, so 80. Let's start with 80, and then let's just resume. And we can see that a bit more was displayed, and now the value that before stops at 64 is 80. So the same value as we wrote here. So okay, let's do another experiment. Let's just reset again and put something even bigger. So let's just put FF, just go full maximum value, and just let's continue. Okay, something mysterious showed up. So I'm assuming this is our flag, but for some reason this flag is not readable for us. This is some kind of gibberish, and we need to now find out how this flag is encoded or encrypted. It depends what's going on, but how to do that. So we can refer back to Ghidra, and we can try to see where this line number, or not the actual line number, or is it line number? let's just focus on this limit. So actually we identify that this is the 319 is the line limit. So this is limiting how many lines we will show. So let's just jump to this and let's see where it's being read. So we have two places. One is here, so this is our call here. So where is the other one? The other one is some other place. Or is it the same place? It's the same place, but a bit later. So it doesn't tell us much where we where it's being used. So we can do something else. So let's just scroll up in our code and let's just do what? Let's just break here at the very beginning, and we can just step through, which is F3 in this debugger. We can just go through all those lines. Okay, we have some loops here, so maybe I will just scroll down a little bit, and I have here something interesting. I have some calls, so I'll put a breakpoint here, and as you can see, we don't have this data here yet. So somehow this data is being copied here, and we just need to find out how it is. So my breakpoint is now here, and I can just go through those calls. And yeah, the fourth call to this 86EC is actually setting this data for me. So this 64 that I'm interested in also is being done by this call to this function. So let me just put a breakpoint here for the future, and now I will break again. I will just reset and run, and I don't need this breakpoint anymore. Okay, and also this breakpoint. Let's just have a clean run. Okay, and I'm here, and I'm stepping over this method, and I'm putting the breakpoint. I'm changing this value to this FF, so I will just compare if it will work. And just after the data is being put here, I can modify it, and I will get the full text as I wanted with this encrypted flag, which I don't know what it is yet. So I'm just resuming, and actually you can already see this was by accident, but we got the flag, and the flag is actually also printed in clear text in the game. So actually when I was doing that, I did not expect to get the flag that soon. I was just wanted to modify the bytes as just before running the loop that will print this text, but I actually got the flag. So I guess the flag is also being encrypted, decrypted by this value. So if we have it 64, I guess it's being this value is being added to these bytes, and if it's FF, we just decrypting this bytes correctly. What we could do, we could just try add a little bit less, so like FE, and see what will happen. So I'm here, I'm stepping over this function, and before, instead of 64, I will put FE, so not FF. And yeah, okay, Ghidra shot first, so it actually also decrypts the flag correctly. I thought it will, not. So maybe it actually checks if it's 64, then it decrypts whatever the value is. But nonetheless, yeah, we got the flag, and it was a bit faster than expected, but yeah, whatever works. So this is how we could get the flag from this NES challenge. So quite nice, not that hard. I don't know whether it was expected to find the flag in this way or not, but this is how I got the flag. So that's all for today. I hope you like it. If so, please like and subscribe, and see you in the next challenge. Bye bye.